will behave. As I was saying in the previous period that are shown there in the blackboard, in general, I have 6 stresses and 6 strains. And because we have selected an orthotropic material, some of these stiffnesses here are very conveniently 0. So in fact, the matrix shown in the blackboard for an orthotropic material becomes this, which is this 3 by 3 portion at the top left, and then only diagonal terms that relate shear stresses to shear strains. So this is the general situation for a single ply or layer that's orthotropic. Now, if you remember from your metals, the equivalent relationships for the 6 stresses and the 6 strains, epsilon x, epsilon y, epsilon z, and the shear strains shown here, gamma yz, gamma xz, and gamma xy. This is what happens for a metal, where everything is conveniently in terms of the Young's modulus and the Poisson's ratio. So the equivalent to this 6 by 6 matrix for a composite, where each term is in general independent of any other, is for metals what's shown here. Now, if the laminate, the stack up of plies, is thin enough, then we make our first biggest and most important assumption for the entire course, which we will actually revisit later on. The assumption that through the thickness there are no stresses. Basically, we say that I have a thin plate. At the top of this thin plate, I have 0 stresses because there is no stress applied. At the bottom of this plate, I have 0 stresses. Therefore, I can assume to a first order that through this thickness here, there is no variation in stresses. In stresses, out of plane stresses, sigma z, tau y z, and tau x z. So if they are 0 at one surface, they will be 0 everywhere else. If I can do that, then the relationships from the previous 2 slides here become significantly simplified, because I have a bunch of zeros for the sigma z, the third equation, tau yz, and tau xz for the fourth and fifth equation. And what that allows me is a couple of things. First of all, I can directly determine the shear strains in out-of-plane. Gamma yz, gamma xz are 0. So that takes care of those 2 equations. There is a single equation at the bottom that relates the in-plane shear stress to in-plane shear strain, which is just well-defined, nothing to worry about. And then I have 3 equations at the top, which are in terms of the 3 strains, epsilon x, epsilon y, and epsilon z. So what I can do now is I can eliminate epsilon z from the third equation here. And I will then be able to write my in-plane stresses, sigma x, sigma y, and tau xy, in terms of the in-plane strains, epsilon x, epsilon y, the 2 normal strains, and gamma xy, the shear strain. When I do the elimination and collecting terms, I will have a quantity multiplying epsilon x in the first equation, which we call qxx, and then a quantity multiplying epsilon y, which we call qxy, and so on, which means I can create a matrix relationship for the stresses as a function of strains in terms of these stiffness terms. So a single ply is characterized by this set of relationships as long as this holds, that there is no out-of-plane stresses. So far, so good? All right. Now, if I take a laminate and I test it, or if I take a single ply, let's continue with a single ply. Let's say I have a single ply with fibers parallel to the loading direction, the top left here. Then I can put a strain gauge on it and measure the Young's modulus. Basically, this plot of stress versus strain would give me, let's call it sigma x and epsilon x, will give me a straight line until it stops being a straight line, but for composites it's almost always a straight line for a single ply. And the slope is the Young's modulus E. So I can measure experimentally the Young's modulus parallel to the fibers from this specimen at the left. Then from the second specimen in the middle, where the fibers now are running horizontally, but I'm loading perpendicular to them, I can measure the so-called transverse modulus, or Young's modulus. And then by doing a shear test, which is not easy, by the way, but by doing a shear test, you get a shear modulus. Also, from this test here, when I apply a tension load in one direction, I can measure with a transverse strain gauge the contraction, or how much it strains perpendicular to the loading, from which I can back calculate my Poisson's ratio. So in general, my Poisson's ratio from this test is minus epsilon 2 or epsilon 1 or let me use epsilon y over epsilon x. So the transverse strain epsilon y is in this direction perpendicular to the loading for this specimen. Longitudinal strain is along the load. The ratio of the two, with a minus sign because one of them is compressive, so I can get a positive value, is my Poisson's ratio. Now this is what I can measure experimentally, and it would be nice to know how this relates to the equation that we just wrote at the bottom here, which characterizes a single ply. So there's QXXs, QYYs, and so on are given by the relationships given at the bottom of the page here. So notice I have the EL, ET, GLT, and the new LT. Now if you had BLT, it would be bacon, lettuce, and tomatoes. New LT is Poisson's ratio. But I also have the new TL. Now that is the opposite of the new LT in the sense that Poisson's ratio new LT means I'm loading in the longitudinal direction, measuring contraction in the transverse direction. If I'm loading in the transverse direction and I'm measuring contraction in the longitudinal direction parallel to the fibers, I will in general have a different Poisson's ratio, new TL. So in fact, there's another Poisson's ratio there, but that doesn't mean I'm adding another unknown. I still am left with 4. Turns out that, and that's mentioned, I think, in the book among other places. If I open this, we probably don't see. It turns out that new LT ET equals new TL EL, which means that the transverse Poisson's ratio, which appears in these equations, is given by known quantities, as shown here on the board. And that, why that happens or why that is true is related to the fact that your stiffness matrix has to be symmetric for a positive definite material and so on. Okay, now everything we said was with one axis parallel to the fibers. In here we had one axis parallel to the fibers in the coordinate system we were dealing with. Well, if that axis, if our reference axis is not parallel to the fibers, we need to know how to transform stress from one axis system to another. So you've seen that before, I'm sure, and if you haven't, you better review it. Basically, if I know stresses in the coordinate system x, y, and I need to determine them in a coordinate system 1, 2, the transformation is here, which involves just cosines and sines of the angle between the x-axis and the y-axis. And that's the standard transformation for a second-order tensor, covered also in the second-year structures course for those of you, some of you, that were with me on that. So that relates stresses from one coordinate system to another, but we also have the problem of stiffnesses. If I have an isotropic material, because the stiffness is the same in all directions, Young's modulus is the same, I don't need to worry about transforming. If in this system, in this material, we have stiffnesses that are different, that means that as I move now to another coordinate system, I need a way to tell me how to find the corresponding stiffnesses in the 1, 2 system as a function of the stiffnesses in the XY system. And you will see that all of a sudden the quantity Q16 and Q26 appear, which are non-zero in general. What do I mean by that? I mean that our basic ply was defined at the bottom of this page, which had to these 2 zeros, which would correspond to the Q16 or to the QXS and the Q26 here. That's because one axis is parallel to the fibers and the other perpendicular. If I have a random axis system, then those terms are no longer 0, and in fact are given by the Q16 and Q26 terms shown here. And M and N are a cosine of the angle and sine of the angle. This is a fourth order tensor, the stiffnesses. That's why everything has fourth powers in the trigonometric values of the angle theta. That means, knowing what we just showed as relationships at the bottom of the page, that you can now write in a concise form the stresses in any coordinate system as a function of the strains in that coordinate system. But this now will involve the Q matrix, which will be a non-zero matrix everywhere. There will be, in general, non-zero entries everywhere. Notice, again, in this case now my fibers are at this weird angle x following the x-axis, and I'm calculating stresses in the 1-2 coordinate system.